Our topic, GCDs and linear combinations. What is a linear combination? I'll take two numbers, A and B, integers, and take two more integers, and we'll form a linear combination of A, B, like so. Typical linear combination. X times A plus Y times B. So I combine A and B using some other integers, positive or negative, add them together. There's my linear combination. For example, let's say A is 355 and B is 115. We can make linear combination like this. Minus 12 times 355 plus 13 times 115. That's one way. 7 times 355 minus 2 times 115. Here, typical linear combinations. Now, the very, very interesting thing about this is like so. If D is the GCD of A and B, then look at this. Then I can express D as a linear combination of A and B. Isn't that a beautiful idea? Let's write it more mathematically. So if D is GCD AB, then there exists two integers, x and y, such that D is x times A plus y times B. Very beautiful. Okay. That's the idea. This is the plan. We're going to try to prove this. Is this easy to prove? Is it easy? And I say yes and no. Okay? It's obvious. I'll show you in a minute why. And maybe not so easy to give an insightful proof. It's easy to give a obvious argument, but not that easy to give a proof that gives you more deeper insight. So let's take an example. Let's take D as the GCD of 355 and 115. Two numbers we did before. This is going to be A, that's going to be B. How do we do this? How do we find GCD? By Euclidean algorithm. Euclidean algorithm, you know how it goes. I express A, I try to divide A by B, integer division, some quotient times B plus remainder, and I can organize this into a table very neatly, like so, okay? And let's start, okay? So 355, that's A, 115 is B. I divide it, goes in 3 times, I do this, 3 times 115 is 345. Subtract that off from 355, I get 10. Now, according to the Euclidean algorithm, this goes here. The new A is the old B. The new B is the old remainder. I do the division again, 11 times. And now I have what? Remainder of 5, right? Okay, one more step. I put this here, this goes here, 5. Okay, 2 times 5 is 10, remainder 0. Right, now when you hit 0, this is the end, okay? And the one right before 0, that's D. There's your GCD. Alright. Okay, now I'm saying here that GCD is expressible as a linear combination of A and B. So is that true? So let's try it. Let's take Euclidean algorithm and work our way backwards. We'll start from D is 5, okay, and we'll work our way backwards and see what happens. Well, let me show you something first. Let's take this A is QB plus R. Now R is A minus QB, right? So I can express my remainder in terms of the other thing. So this is the remainder. I can express this remainder in terms of these numbers here. Alright, so D is 5, and I do this for this row. So I get 115 minus 11 times 10. Okay, what is 10? Let me work backwards to this 10 here. Okay, let's work backwards. Now I can plug that in. I do the same idea. I apply this concept again here. I calculate this remainder in terms of these numbers. So I get 115 minus 11 times, now 10 is 355 minus 3 times 115. See? Okay, compare this with this, alright? See, get R, solve for R. Plug it in here, get rid of the 10. Now I have 115 minus 11 times 355 plus 33 times 115. I end up with minus 11 times 355 plus 34 times 115. Yes, okay, now this is 3,905 minus 3,905. That's 3,910. Total is 5. It works. So I have, watch this, I have expressed D in terms of a linear combination. Minus 11 times 355 plus 34 times 115. This is A, this is B, this is X, this is Y. And all are integers as I promised. So it works. So, you know, it's obvious that this works. And it's obvious that it will always work. I will always be able to express this in terms of this and this by working backwards. I can always do this. The thing is how to prove this. Like we know it's true by intuition. Now many proofs I've seen actually construct Euclid's argument here backwards. They do some kind of induction or they arrange an algorithm that goes backwards until they find these numbers x and y, and they prove it in the general case. Now, I already know that that's true. I say that that's obvious. So I'm looking for a different kind of proof. I don't want to just take Euclid's algorithm and go backwards like it is done in many books. That's interesting to do, and I might do a video on that later. But I want something more insightful. So the obvious way is Euclid's algorithm backwards. I don't want that. I want something which gives me more insight. And that way is group theory. This is the approach we're going to take. Starting in the next video, I'll introduce the idea of groups and we'll use it to prove this problem here, or this concept, that the GCD is always expressible as a linear combination of the two numbers. It's a very, very powerful, very important idea in mathematics. We will use it to solve many other problems. Okay, see you later. If you like this video, click like, subscribe, leave a comment, and hang on for more of GCD and linear combinations.